I've said before that a nerve impulse is an electrical signal that travels along the neuron, but it's not quite electricity as you may know it. Electricity is the flow of electrons, but in a nerve impulse we use the word potential to describe the movement of charged particles across the membrane of a cell. The charged particles flow like a wave down the axon, moving in and out of the cell. The movement is mostly of positively charged ions, not negatively charged electrons like you might imagine. Let's look even closer at the cell membrane. At rest, when a neuron isn't firing, there's a high concentration of sodium ions outside of the cell membrane, and also a high concentration of potassium ions in the cytosol of the cell. The sodium and potassium channels are gated and closed. Because of the difference in number of sodium and potassium ions, as well as the presence of negative ions like chlorine, there's an overall negative internal charge of negative 70 millivolts. The beginning of an impulse is marked by depolarization. This means that the voltage-gated sodium channel is opened and the sodium rushes into the cell. The influx of positive charges quickly shifts the electric potential of the membrane so that now the outside is more negative and the inside of the cell is more positive. This change in polarity will close the sodium gate. Nearby is the voltage-gated potassium channel, which will now open and allow potassium ions to flow out of the cell. The movement of these positive ions will repolarize the cell, allowing the cell to have a negative internal charge relative to the positive extracellular charge. The change in polarity will also close the potassium gate. At this time, you might think that the cell is ready to receive another signal, but it can't. If the sodium gates opened, the sodium ions would not move. In order for ions to move through their channels, they have to be able to move down the electrochemical gradient. The positive sodium ions aren't attracted to the positive environment outside of the cell, so they won't move. Another signal can't be sent until the sodium and potassium ions have moved back to their resting potential positions. But this means moving against concentration gradients, which means energy must be used. During the refractory period, the sodium-potassium pump will move 3 sodium ions out of the cell and 2 potassium ions into the cell with 1 ATP molecule. This must happen constantly and rapidly, so the brain uses a significant amount of your body's energy. In a matter of milliseconds, the sodium-potassium pumps will restore resting potential and another action potential can move through. Nerve impulses are actually waves of action potentials, which means ions are flowing in and out of the cell in a wave-like pattern. Because of the refractory period where sodium ions will not flow out of the cell by diffusion, action potentials can only move in one direction. They begin at the dendrites and they end at the axon terminals. This wave-like region where the action potentials are flowing are referred to as the local current. The flow of sodium through one gate will trigger the flow of sodium in the next gate, but sometimes there isn't enough sodium to trigger an action potential. Using an oscilloscope to display the membrane potential over time, we can see that sometimes the flow of sodium ions isn't enough for an action potential to occur. The internal region of the cell must reach negative 55 millivolts, the threshold potential, for action potentials to begin. If enough sodium ions are released to surpass the threshold potential, an action potential occurs. In the oscilloscope trace of an action potential, we can see where the sodium and potassium gates have opened. Here is the point where the stimulus occurs, and sodium gates open, allowing sodium to rush into the cell. This depolarizes the cell, causing the inside to become positive relative to the outside of the cell. This polarity change opens the potassium gate, which allows potassium ions to rush out of the cell, which rapidly repolarizes the inside to a negative charge. This can often become more negative than negative 70 millivolts and is called hyperpolarization or undershoot. This will be corrected during the refractory period, where the sodium-potassium pump uses ATP to restore resting potential. During this time, no additional action potentials can be sent, but once resting potential is reached, the neuron is ready to fire again. Thanks for watching this episode of Teacher's Pet. Don't forget to like and subscribe and follow me on Twitter @SciencePet.